Recording is rolling. It is Wednesday, September 25th. Let's take today to focus on solving textbook puzzles. So for you guys remember I gave this, I think last week. So chapter 4, this is in two parts. There's some warm-up questions, which is the front page, and then there's like the main puzzles here. Of course, you guys have all the solutions, and I want to walk through a bunch of those today. Okay. You guys know there's a hurricane headed this way, sort of. I was thinking it was going to miss us, but now I'm looking. All right. I think we're going to know by the end of today whether or not there's going to be school the rest of the week or not. There's no official word yet. Last I checked. So, guys, if there is school tomorrow, then I have an Atwood lab lined up. It's a paper that you guys already have. You guys remember the friction lab yesterday? It's just printed on the opposite side. All right, so we're gonna take some string, put it over these pulleys, take some lab weights, hang them. They'll look like this. One of these two setups. Right, here's the classic Atwood. Here's the modified. Slip a little hot loads part here. Right, so won't quite touch this today, but just be ready for that. If there happens to be a school tomorrow, we're gonna be doing that. Right. Guys, if there's no school the next couple, I might not see you guys possibly until Monday, maybe. Right. So, guys, take the next few days to make sure you're all up to speed with all your classes. Check focus, make sure you've got everything in. For example, in this class, I'm still waiting on some projectile quizzes. Also, you guys remember that AP Classroom, the kinematic motion? I've still got a few students who haven't done that. Every few days, I'll check and see if you can still turn in late as long as you turn in. Maybe some of you guys possibly just didn't hit submit. Sometimes some students do it and they just don't hit submit. From my point of view, it looks like you didn't do it at all. Just hit submit and then I can put the points in for you. Okay, so guys, there are lots of the only ones I'm gonna just check and score are just the ones I circled. You guys see I circled some of these that you can more focus on. But if you want lots of extra practice, there are lots of other good questions here. Like this one I didn't circle, but I know it turns into a quiz question past. It's got to get passed, right? But, all the ones here are really classic physics questions, right? So the ones I circle are just kind of a minimal starting point that I'm just going to score for homework puzzles. Guys, don't forget too. AP Classroom has a bunch of daily videos. I never specifically assigned this, but if you need a little bit of simple instruction, you guys got maybe a different point of view, different perspective you guys can see from those videos. Okay. All right. So let's hop into it. All right. So remember the solutions I uploaded to Google Classroom. Here's the way we're going to do this. I'm going to pull up those solutions here in a moment on my computer screen. And I'm going to show you guys the forest for the trees roadmap of how to think about these puzzles and solve them. Okay. And then I want to give as much class time as possible for you guys to work independently, and I can walk around and help you guys out individually. If you look at my solutions, do you guys bring your laptops today? Yeah, I see some of you guys have your laptops. That's probably a good idea. Have your laptops ready to go so that as you solve them, if you're really, really stuck, you can check the solution and see how to solve it. And if you're still stuck, you say, well, where's he getting this from? Then you can call me over and I could definitely help you out. Right? So that's the plan. That's the way we're going. All right, so switch my screen here. All right, so here's the solutions. Look at them. Right, so let me go ahead and scroll down. Guys, I'm just gonna right now point out the ones that I've already circled. So it looks like the first one I circled is the warm-up number 2. So this is part A, the warm-up. We scroll down to number 2. Okay, just point out how to solve this. So it says 4 forces act on an object. We got north, south, east, and west. And I went ahead and put them here. Do you guys see 4 force vectors? And I labeled them all. Now, guys, how to think about this is, do you think there's a net force horizontally? Maybe subtract the 2, right versus left, they subtract. And there's a net force vertically, and then looks like it's pulling south more than north, right? So, okay, so you find what's the net force east-west and the net force north-south, right? And then you can put it together with Pythagorean theorem. Furthermore, Pythagorean theorem only tells you the magnitude of the net force. Remember, the net force is as if there's a single force acting on it. Yeah, there can be a bunch of individual forces, but the block can only move one way as a result. It can only accelerate one way. So as if there was a single force acting on it. Now, the Pythagorean theorem will tell you the magnitude. But guys, how do you get an angle? How do you solve for an angle? Inverse sine, inverse tan. Either of those could work depending on what 2 legs of a right triangle you're looking at. Right, here, I'm going to skip along here. See, I did not circle number 3. Oh, these are all good questions. Number 4. Okay, guys. All right. You know what? If it was a different day, I may or may not have circled this one, but it looks like I did. So let's run with it. Guys, there are lots of time in life. I remember this coming up in college a few times, where sometimes you'll be handed an equation out of the blue. You've never seen it before, and you're said, a apply this equation or tell me something about it or solve something proportional, right? This is one of those. Guys, this equation has not come up in this class yet, but you're seeing it for the first time. Let's do it. It says something about the gravity field of a planet. Now, guys, here's how you get, you guys know there's a gravity field holding you on the surface of the Earth right now, and it's different on different planets. Where does that number come from? Now, this is a future topic, but you're getting a sneak preview right in here. It goes like this. Take the mass of the planet, divide by the radial size squared. Talk about this in a few weeks, right? And then you guys see this capital G here. This is called a universal gravitational constant. Nobody knows why it is what it is. It's just been measured to be this number, right? You can put it all together, right? So if you pop in here the mass of the Earth and put the radius of the Earth here and universal gravity constant here, and you run the numbers, guess what number pops out of this equation for Earth? 9.8 meters per second squared, exactly. So the question they're asking is a proportional question, saying, well, what could the gravity field be on the surface of the planet? Suppose it had twice the radial size of Earth, but also twice the mass, right? And if you run the number, you guys have run plenty of proportional type questions in this class, so you've seen this type of question plenty of times, right? Now let's just apply it to say like a new type equation, right? Skipping down here. No. Oh, hey, look, it's the chain gang. It's the monkeys. I did not circle that one. Maybe I should circle that one, but right. This one I did circle. Number 6. You guys see that block hanging from a couple of strings, tension strings? So the way to approach these, I think it's circled a couple of these, is look at the point where all the strings come together. This point here. I see a force up to the left, a tension force up to the left, tension force up to the right, and I see a weight down. Right. Now, isn't it true that if it's hanging in equilibrium, all those forces have to zero out? Right? So introduce a Cartesian system, and this one pulls left and this one pulls right. I've got tension to the left, sine 30 degrees, tension to the right, sine 30 degrees. Hey, look at this. Some of the forces in the x direction zeroes out, so I got that zeroed out. Now, since this has some horizontal symmetry, that piece you can already get to this. You can say, oh, well, the tensions have to be equal, which you could probably kind of stand back and eyeball and figure that was probably going to be true anyway, just from this particular setup because it's symmetrical, right? But here's how you can mathematically show it. But you need another equation. You need a vertical equation. So this up, this down, all zero out. So really you have a system of equations. Right? Here's one equation here. Here's another equation here. Okay. And then you could do a substitution. See, I did like a substitution, right? And then bam, I got the tension. Right. Again, see, in a few minutes, you can pull out a blank piece of paper and do this completely from scratch on a blank piece of paper. Right. And if you really get stuck, you can take a glance at my solutions. It'll tell you exactly how to solve it. That's true for all these. I should have circled number 7. It sets up 4 different scenarios to solve for the normal force. Right? Anyway, that was a pretty good one. What's the next one I actually circled though? Is number 10. This one we got a block sliding to rest, and they give you a coefficient of friction, and they ask a bunch of questions like they ask how far does it slide? I think, yeah, they ask how far does it slide given the coefficient of friction. Suppose this was like a hockey puck, and there's a little bit of friction going on. Okay. Do you guys see? Okay, so here's all the given values: the mass, the gravity field, the coefficient of friction. Hey, does this look kind of like your lab yesterday? I bet you guys are getting coefficient of friction of about that number, pretty close right there, right? The friction force could be about 30% of the normal force, right? Oh, they also gave an initial velocity. So you guys see we're mixing and matching dynamics and also going back to kinematic motion, right? You guys remember the kinematic bridge poster, right? You guys remember that one? So here's an equation straight from your lab yesterday. Boom, boom. Solve for the force of friction. You can take that, go into Newton's second law of motion, solve for the acceleration, then kick back over to kinematic motion and figure out how far it's going to slide before it comes to a stop. All right, so the next one I circled is, number 13. Wait, did I? Here it is. Wait, is this right? Yeah, this is it. Do you guys see number 13? There's 2 blocks being dragged and there's a string holding the blocks together and they're being pulled horizontally. Which is actually kind of similar to the monkeys hanging on a vine question that I didn't circle that you guys saw earlier. Isn't this just the chain gang question turned sideways like a train? Sometimes this is asked as a train, right? There's an engine pulling a bunch of boxcars behind it. What's the tension in the links? Something like that. It's the same type of question. So you can solve those Newton's second law of motion. Say, well, whatever strings are in front have to pull all the blocks behind them. That's a lot of mass. That's a lot of tension force. But as you go back further, they each have to pull less and less mass blocks, and so it's going to be smaller tensions. So you can see it, right? Let's see. All right, there's a bunch more questions that are all good questions, but I did not circle any more of the warm-ups. I think you guys have seen some. Oh, actually, here, while I got this up, let's hit this real fast. Okay, suppose there's 2 guys playing tug of war. Two guys playing tug of war. You guys see this? All right, I didn't circle this one. Let's do it right now anyway. Suppose this guy's pulling to the left with 200 newtons of force. This guy's pulling to the right with 200 newtons of force. What's the tension in the rope? 200 newtons, right? Like if you cut the rope and put a little spring scale in there, it would read 200 newtons. So it's 200 newtons everywhere. Because some students say, well, it's 200, 200? Does that make 400? No, it's just 200 everywhere. Okay. Right. Hey, what's the friction force between this guy's feet and the ground? 200 newtons, right? Right. Okay. All right. So that's all from that one. Let me flip over to all right, part B, which is just the next page. Right. So I circled some of these. I'm gonna get here. I'm just gonna do a few of the ones that I circled here, just to get you guys set up. So number 7, it's a guy in an elevator. Guys, don't I have a couple of posters for people in elevators? There's one that's a whole proof written out for accelerating upward, which actually pretty much this puzzle right here is one of the posters. Right? It's oh, okay. You guys got that in your thumbnails, I think. All right, what else we got? Number 10. I did circle this one. So you got a bullet and a rifle. Right. Ooh, let me ask my own question here. There's a bullet and a rifle. There's pow, explosion. Sends the bullet out to right with some force, some blast force. Now I'm doing a free body diagram sort of just on the bullet. Guys, is there also a force back on the rifle that I did not draw? Right. Guys, which force is bigger? The force pushing the bullet forward or the force pushing the rifle back? Same force, equal. That's Newton's third law. Right. The free body diagrams typically just focus on a single object, in this case, the bullet. Right. It asks, what is that force? But it starts with, right, it's going so fast. Hey, is this a kinematic to dynamics bridge right there? Right, go through acceleration. Right, so also I got number 15. There's a ball bouncing. A few weeks from now, you guys are gonna do a lab that looks kind of like this, where you're like bouncing balls off the floor. There's a drop height and a rebound height that's gonna be shorter. That makes sense. It's gonna rebound not as tall. Right? All right, now guys, stepping through this one. Do you think that you could solve for the crash speed based on this drop height and the rebound speed based on this rebound height? And that could be, that's kind of like, that's kinematic motion there. You guys remember this kinematic equation right here? Right, so like the third kinematic equation, and you can solve for those crash speed and rebound speed. Now the actual question is, what is the force on the ball? You need to know one more thing to solve for the force, or sorry, 2 more things. You need to know the mass of the ball, which is right here. You also need to know the time interval of that collision, which is a tiny, tiny fraction of a second. Do you guys see 2 milliseconds right there? I turned it into seconds, right? 0.002 seconds. Okay, so that's what I'm saying. Okay. There's enough information there. You can apply Newton's second law of motion, and I showed you guys how to do that, which is actually really similar to an equation you're going to see later in class called the impulse formula. It's basically almost the same thing. All right, one more I want to go over right now. That's number 19. It's the bird feeder. Do you guys see the bird feeder on? Here we go, 19. Hey, we're back to, here's the bird feeder, has a weight. I think they told you the weight is 150 newtons. There's 150 newtons. Guys, side question. What's the mass of the bird feeder approximately? How many kilograms? 15. So 15 kilograms weighs 150 newtons about, right? Pretty close. If I round gravity to about 10 meters per second squared. All right. So I don't think that comes up in this, but just aside that. All right, so we got a couple of ropes tension, but this time it's not symmetrical. Ooh, do you guys see there are different angles? So here in circle, I put this in tiny ink. I was trying to fit it on a single page, but it's all here. What I circled right here is the system of equations. You guys see? And there's 2 unknowns. What's the tension in the left string and what's the tension in the right string? Guys, if you have 2 independent equations and 2 unknowns, is that solvable? Yep. Right, as long as the number of independent equations matches the number of unknowns, it is solvable. Right, here it's 2 and 2. Right, I got a horizontal equation, a vertical equation. I have to break these into components. You see that? Right. So it's a little trickier than one you guys saw earlier. That looks kind of like this. That was symmetrical. This one's asymmetrical. Right. But you could do a substitution. You guys do substitutions in algebra class. It shows you exactly how to do it here anyway. Right. So continue here. Right. Once you get one tension, then you can take the go back to one of these equations in your system of equations. I pick this one right here and say, well, here's how one tension relates to the other tension. Do a substitution, bam, get the other tension, like that. All right. Now I did circle some other questions, but the ones after this look like Atwoods. You guys see some Atwoods? So that's going to take us to tomorrow. Maybe I want to kickstart that off with a lab. You guys do the lab first, and then we'll go back and I'll show you guys how to actually solve the Atwoods through dynamics. All right. So with that, oh, good. We have a solid 31 minutes in here. Great. This is perfect. So go ahead, have some paper out, solve as many as you can, and I'm going to walk around, help you guys individually troubleshoot any specific questions that you guys have. That's a wrap on this video.